Let's talk more about finding the area under a curve using the limit definition of the integral. So there's a couple of things I want to say just so they're aware of them. We'll look at two examples to start, and then we'll kind of talk about some other stuff. So let's say we want to find this integral. We'll make it not terrible here. Yeah, let's make it not terrible. From 0 to 2 of x squared plus 4x dx. So when faced with something like this, we want to rewrite it as a limit of a sum. There's a couple ways to do this, but the easiest way usually is using the right-hand endpoints. So we're going to swat at the bug up here. We're going to write this as the limit as n goes to infinity. And we'll talk about this a little bit more. In the next example, we'll talk about how this is the same thing as the norm of the partition going to 0. But oftentimes, if our partition is what's sort of regular, where each interval has the same width, we just say we let n go to infinity. This is going to be the sum from, I forget, we're using i's or k's. Not that it really matters. We could use j for all I care. I'm going to use k, right? Was it k? Sorry, both classes I'm teaching are doing this. One class is using I, one class is using k. So I'm like, what are we doing in this class? Again, really, you should be able to use anything. I, j, k, m, n. We'll use k. From 1 to n of our f of x sub I. So over here, let's write down real quickly. Our delta x is 2 minus 0 over n, which is 2 over n. And our x sub I, which is the right endpoint of the ith interval, is just going to be your a plus I times delta x, which in this particular case is 0 plus I times 2 over n, or 2I over n. So then this part here, and when I look at this, I'm really thinking of how the integral is becoming the summation symbol. The integrand, which is f of x, is becoming f of x sub I over here, which in this case is going to be just the function x squared plus 4x with this 2I over n plugged in. So it's going to be 2I over n squared plus 4 times 2I over n. And then times, and I should put some parentheses around that, my dx, which is my delta x, which is going to be 2 over n. But there's kind of a very natural correlation. Integral symbol becomes the summation. The function here becomes the function there. The dx here becomes the delta x there. So all those things should show up in your limit definition of the integral. The rest of this is mostly just messy algebra. But let's do it. So I'm going to multiply this out, and I'm not going to show a lot of work. So I'm going to write this as the limit. Oh, so I did the thing. I made an error. You can call it an error. I'm clearly used to using i's instead of k's, because even though I said k, I started writing things with i's. So let's just make it not terrible and say that we're using I here instead of k, because clearly I want to use I, not k. So we went from I equals 1 to n instead of from k equals 1 to n, because we used i's, not k's. Either way is fine. So we're going to write this as the limit as n goes to infinity of the sum from I equals 1 to n. And we're going to multiply this out. So let's see. 2I over n squared is 4I squared over n squared times 2 over n is going to be 8I squared over n cubed. 4 times 2I over n is 8I over n. And then times another 2 over n is going to be 16I over n squared. I'm happy about this. Why? Because the power of I is 1 less than the power of n. It's always what I'm looking for in each one of my fractions when I'm doing this kind of problem. If that doesn't happen, then I'm probably made some sort of algebraic mistake multiplying it. We're going to break this up. We're going to write it as the limit as n goes to infinity. I'm going to pull out constants. So I'm going to have 8 over n cubed times the sum from I equals 1 to n of I squared plus 16 over n squared times the sum from I equals 1 to n of I. And the reason we are doing that is so then we can use the formulas for the sum of I and sum of I squared, or the sum of whatever thing you've got. In this particular case, we have the limit as n goes to infinity of 8 over n cubed times the sum from I equals 1 to n of I squared is going to be n times n plus 1 times 2n plus 1 over 6. Plus, here we're going to have 16 over n squared times the sum from I equals 1 to n of I, and the formula for that is n times n plus 1 over 2. Then if we want to show as little work as possible, and I do really want to show as little work as possible here, I can see that if I were to multiply out the top here, I would get 8 times 2, I'd get a 16n cubed on top and a 6n cubed on the bottom. So the limit of this part here is going to be 16 over 6. The limit of this part here is going to be 16 over 2. So then we're left with 8/3 plus 8, which we could write as, what, I don't know, 24/3 plus 8/3, so 32/3. So the work I'm not showing that maybe, and which we'll show now, but the work that you're going to often see people kind of be like, yeah, whatever, is when I did this limit here, the limit is n goes to infinity of 8 over n cubed times n times n plus 1 times 2n plus 1 over 6 plus 16 over n squared times n plus 1 over 2. A couple ways to show the work here that makes this easier. You can cancel an n here and an n here. So then I really have the limit as n goes to infinity on top of 8 times n plus 1 times 2n plus 1 is 2n squared plus 3n plus 1. On the bottom, I have 6 times n squared. Plus, here I can cancel an n as well. And I've got 16 times n plus 1 over 2n. Multiplying it out, we get the limit as n goes to infinity of 16n squared plus 24n, plus it doesn't really matter, over 6n squared, and then plus 16n plus 16 over 2n. And now we're seeing, oh yeah, we've got quotients where the degree on top and the degree on the bottom are the same, so the limit's the quotient of the leading coefficients. Same deal over here. The degree on top is 1, the degree on the bottom is 1, so the limit of that part is the quotient of the leading coefficients. That's how we're getting those values. Yeah. Sorry, can you speak up a little bit? Well, we haven't done the limit yet. So even though we're writing the limit every time, we're kind of ignoring it. We're saying, yeah, we're not really thinking about the limit being there. It kind of isn't there. And so right here, as far as this summation is concerned, the 8 over n cubed doesn't matter. In fact, let me show you, because I think that's a really good question that we kind of just gloss over. If I have the sum from I equals 1 to n of 8n cubed times I squared, I'm going to write it out long way. So I plug in 1, I get 8 times 1 squared over n cubed, plus 8 times 2 squared over n cubed, plus 8 times 3 squared over n cubed. And I bet you all can start to see where this is going to go. Every term I'm writing, even up to the very last term, 8 times n squared over n cubed. I don't want to cancel n's there, even though I could. Every term, what could I factor out? What's one of the things I could factor out? My favorite number, 8. What else? The 1 over n cubed. So I could rewrite this as 8 over n cubed times 1 squared plus 2 squared plus 3 squared plus 4 squared plus all the way to n squared, which then we could rewrite as 8 over n cubed times the sum from I equals 1 to n of I squared. So that's really what allows us to do that. Is as far as this summation is concerned, the only thing that's actually changing is the index I, or k, if we use k, not n. N is a quote unquote constant. It's just the number of subintervals we happen to divide this up into. And then after we have dealt with the summation part, then we take the limit and let the number of subintervals get larger and larger. Other questions about this? Yeah. Mm-hmm. Manual zoom here. Maybe. I said yes confidently, and now we'll see. Is that a little better? Cool. If I do get off screen, let me know. I will try to make sure what I'm writing is on screen, but this is not quite showing everything. So
Right.
did I let's see. So right here. So right here we're using the fact that if you take the limit as n goes to infinity, right? It's the limit of all of this. So specifically for this part here, the shortcut is to say, oh, everything, I should say, the numerator and the denominator have the same degree, so the limit ends up being the quotient. But if you want to do it the long way, well, actually, you could go one of two ways. You could either use L'Hopital's rule, because technically you have an infinity over infinity indeterminate form. It seems like overkill to me, though. What I would do is divide everything by the highest power of n in the denominator, and get the limit as n goes to infinity of 16n over n plus 16 over n over 2n over n, which simplifies as the limit as n goes to infinity. Can you all see that? Yeah. I should look right there because it's literally in front of me, except to look there, not there. Okay. I'll learn one day. 16 plus 16 over n over 2. And the 16 over n does what as n goes to infinity? Right. So what are we left with? 16 over 2. Right. So you're perfectly allowed to say, to use the shortcut here and just say the limit is 16 over 6 plus 16 over 2. Other questions about this? All right, we're going to do another example, which is maybe somewhat atypical for me. Fine. So we're going to do another one of these where we're going to, let's make sure. So if you can't see things, let me know. So we're going to evaluate, I should look right there, the integral from 0 to 1 of the square root of x dx using a Riemann sum. How can I spell? Maybe. But now our partition, so we're going to use a partition here. We're not going to use n equals sum intervals. We're going to break this up into very convenient partitions, for this particular function. So with right endpoints, sometimes the spelling gets away from me, endpoints, and the partition is given by the following. So our partition, which we're going to label P sub n, is going to be these points, 0, leftmost endpoint. And then we're going to have, I'm going to write this kind of in a silly way, 1 squared over n squared. I know it's 1, but I'm trying to emphasize what things look like. The next endpoint's 2 squared over n squared. The next endpoint is 3 squared over n squared. Hopefully you can see where the pattern is going here. All the way to, okay, I'm going to try to use k this time and not I. K minus 1 squared over n squared, k squared over n squared, all the way till the very end, which is going to be n minus 1 squared over n squared. And the very last one is 1, which is n squared over n squared. So we're breaking up our interval from 0 to 1 into n subintervals, but they're not equal width. Let's draw it. We're starting at 0, we're ending at 1. And so if we start drawing things, my first width is pretty small, 1 over n squared. And my next one's going to be a little bit bigger. How do I know it's bigger, actually? Well, let's think about it. The difference between 0 and 1 over n squared is 1 over n squared. The difference between 1 over n squared and 4 over n squared is 3 over n squared, which is certainly bigger than 1 over n squared. And the next one would be over at 9 over n squared, which is still a bigger difference yet. The difference between 9 and 4 is 5. In fact, every difference is going to be just the next odd number. So the next one would be 16 over n squared, which would have a difference of 7. So every time I do one, it's going to be bigger. Up until the very last one, which is going to be n minus 1 squared over n squared. So let's find the norm of the partition. I have to add this in. So anyone ever seen Cheers? Am I really dating myself here? I think I'm really dating myself. Okay, well, you're missing out. It wasn't that good a show, but there was a guy named Norm. He walked in the bar and was like, Norm. Anyway, that's what I think of when I think of the norm. But really, the norm here is the length of the longest subinterval in our partition, which we can visually see here has to be the rightmost subinterval. It is the longest subinterval of all five, of all of them. There's not five, there's more than five. So the norm of the partition, which we're going to write as this, the magnitude of P is probably what I would say. I like the word magnitude better, but norm is fine. You'll definitely see this again when you take 21C, I think, when you talk about like vectors and finding the length of a vector or the norm of a vector or the magnitude of a vector. This notation is often used. So the norm here is going to be whatever that length is there. So the norm of P, which again is just the length of the longest subinterval, is going to be 1 minus n minus 1 squared over n squared. So let's be smart and write that as n squared over n squared minus n minus 1 squared over n squared. And we can simplify that a little bit. That's going to be n squared minus n squared minus 2n plus 1 over n squared, which is going to be the n squareds cancel. We get positive 2n minus 1 over n squared. Cool. And then you can say, well, we're going to find, so let's actually, we'll back up. We'll come back to this. So this is the length of the longest of the norm of our partition. Most of the time, we're not going to use limit definition this way. Most of the time, we're just going to use right endpoints because it's convenient. But here it's convenient to do this way. So let's write our integral. So we're going to write our, oh, we have to be a little bit careful here, right? Because we're not just going to do limit as n goes to infinity of the sum of the right endpoints. So let's actually write down what this thing looks like. No, you may want a little more room. Yeah. So I'm going to try and draw this function here. Start at 0. Here's my good square root function. Yeah, looking good. And I'm breaking this up into my partition here, which looks like, sure, we'll go to the kth one there. We'll go to the last one. And sorry if things don't look like they're exactly maybe the right length. So here's our first point, C1, which is going to be 1 squared over n squared. Our second point, C2, hopefully you can see it all right. Yeah, that looks all right, which is going to be 2 squared over n squared. C3 is going to be 3 squared over n squared, all the way to the, so again, here's the first one, the second one. We're using those to find the areas. I'm drawing some rectangles, the third one. All the way to the kth one, where this part here is k squared over n squared. And this part here is k minus 1 squared over n squared. So the height here is going to be given by this endpoint there. Still using right endpoints. They're just not equally spaced apart. And then all the way to the last one over here, which is going to be n squared over n squared. Question? Well, the purpose is that we have picked something that works out specifically perfectly, so then when we actually try and find the sum, we can do it. So that's why we've picked these specific subintervals, because in a second, we're going to see that when we plug them into the function, the square root of x, things are going to work out nicely. So that's why we picked an atypical partition here. So let's go ahead and find the area, the integral from 0 to 1 of the square root of x, by writing this as the limit as our partition, sorry, the norm of our partition gets smaller and smaller and smaller. And then it's going to be the sum from k equals 1 to n of the usual kind of thing. My base times my height. And let's just do it for the kth the kth rectangle here. So for the kth rectangle, my height is going to be f of, I stopped labeling these things. It's going to be f of k squared over n squared. And the base is going to be, well, the base of this just like the base of the nth one was 2n minus 1 over n squared, the base of the kth one is going to be 2k minus 1 over k squared. Over n squared, sorry, not over n, not over k, over n squared. Oof. Let me show that because I feel like I'm maybe being a little hand wavy here. If we subtracted those, k squared over n squared minus k minus 1 squared over n squared, that's also going to give us 2k minus 1 over n squared. Yeah, that seems okay. Right, you multiply that out, you subtract the k squared to cancel, you get a minus 2k plus 1. Yeah. Yeah. All right, so then our function here is the square root. So this is going to be the limit as our partition, sorry, the norm of our partition goes to 0 of the sum from k equals 1 to n of the square root of k squared over n squared times 2k minus 1 over n squared. Observe the norm of p being equal to 2n minus 1 over n squared. If this is going to 0, well, let's rewrite it. This is really equal to 2 over n minus 1 over n squared. The only way for that to go to 0 is if n gets larger and larger and larger. So typically, the norm going to 0 means the number of subintervals has to get larger and larger and larger. There's no other real option. So the norm of our partition going to 0 still means that the number of subintervals has to go to infinity. So we're going to rewrite this next step, replacing the norm going to 0 with the limit as n goes to infinity of, look what we've got here, the sum from k equals 1 to n of the square root of k squared over n squared, k over n, times 2k minus 1 over n squared. Let's see what happens. Now we're looking like something. Now, I will point out, this one is kind of, for lack of a better word, breaking one of the rules that I like to try to adhere to. Most of the time, I would love for each thing to have a 1 less power of k over a 1 more power of n. That's usually what I'm looking for. That's not going to be true here. It's okay, sometimes it happens. So I should really say the thing that I look for to happen always happens when your functions are polynomials. So like all the things we've dealt with, like 2x plus 7 or 2x plus 1 or x, right? Anything with a positive integer power of x, the thing I said will happen will always happen. But otherwise, it's not guaranteed. We just don't usually look at examples with that. Looking here, we're going to get the limit as n goes to infinity of the sum from k equals 1 to n of 2k squared over n cubed. That looks promising. But then we also have a k times negative 1 over n cubed as well. I'm still going to do the usual thing of breaking this up and pulling out the constants. So I'm going to write this as the limit as n goes to infinity of the constant for this first one is going to be my 2 over n cubed times the sum from k equals 1 to n of k squared minus 1 over n cubed times the sum from k equals 1 to n of k. Use our formulas. Whoops, we still have a limit. Limit as n goes to infinity, 2 over n cubed. The formula for the sum of the squares of the first n terms is still n times n plus 1 times 2n plus 1 all over 6 minus 1 over n cubed times the sum of the 1 plus 2 plus 3 all the way to n is going to be n times n plus 1 over 2. All right, everybody should take a minute and finish this limit. Oh, yes, I can move the paper back down. Oh, that was like 16 minutes ago. So if you're on Zoom and you have a question and I don't seem to be addressing it, it's because I haven't seen it, even though my computer's right in front of me. You're welcome to unmute yourself and say words. Feel free. What's up? Sure. Where's the graph? I don't know. I think, you know, I'll post the notes later. You're welcome. Right, so the limit of this part, I see a 2 times 2 times n cubed on top and a 6 times n cubed on the bottom, giving me the 4, 6. Over here, I see a highest power of n squared on top and a highest power of n cubed on the bottom, which means the limit of that's going to be 0. Because when the degree on top is less than the degree on the bottom overpowers the top and the fraction just gets closer and closer to 0, or smaller and smaller and smaller. If you think about what this actually is here, that's going to be n squared plus n over 2n cubed. And if you break this up as n squared over 2n cubed plus n over 2n cubed, that's going to be 1 over 2n plus 1 over 2n squared. And that's definitely going to go to 0 as n goes to infinity. So if your degree on top is less than your degree on the bottom, it doesn't contribute anything. So you end up getting a final answer of 2/3, which is actually the area under the square root function from x equals 0 to x equals 1, which we will see a little bit later after we talk about the fundamental theorem of calculus. And here's, just in case you're, here's the, I think, is that the picture you're looking for? Maddie? Was that the picture? Oh, sorry, I'm zoomed in. Apologies. I keep thinking you can see the thing that I'm seeing. There's that picture.
Like where you change the partition from 0 to n to a fifth, we can assume that.
Yeah, that's pretty generally true. If the norm of your partition is getting closer to 0, typically that means the number of partitions has to be getting larger and larger. There isn't really a way. It was given to me. So right, like usually we're not going to be asked to come up with a special partition to make ones that are not polynomials work out nicely. And it is moderately is probably an understatement, challenging to find the right partition for functions that are not polynomials. There is an example how you can find like the area under the sine curve using a regular partition and some wacky formula for sine of some stuff equals some other stuff. I couldn't tell you what it was, but it is possible to do these limit definition of the integral used for functions that are not polynomials. It's just you need a lot more machinery. You need the right partition, or you need a special formula or something else. Most of the time when we're actually doing these as students, we are limited to just integrating things that have like constants, x squared, x cubed. That's kind of the up. I mean, you could go higher, but then they'd have to give you the formula for the sum of the first and fourth powers of your thing, or fifth powers, or whatever you would need for that. I saw another question. Yeah. Sure. So I'm using, and these are formulas that I imagine you were expected to memorize. Where I'm using the formula that the sum from k equals 1 to n of k, which is just 1 plus 2 plus 3 plus 4 plus all the way to n. That formula is n times n plus 1 over 2. Similarly, just to kind of be complete here, the sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 divided by 6. And then the third one, which I believe you were also expected to know, is if you add up the first n cubes, it's going to be n times n plus 1 over 2 squared, which I think is super cool because it's just that formula squared. So if you know that one, you know that one, which is great. Okay, let's take a look here quick. Yeah, that seems good. All right. So yeah, let's do that. So eventually we'd like to be able to find area under a curve without just having to use this limit definition of the integral to find the area. So we might start asking questions like, what's the integral from 0 to 6 of the square root of 36 minus x squared? which you can barely see. There you go. So the thing to know about this is when someone asks a question like this, all they're asking you to do is to find the area under that curve between x equals 0 and x equals 6. And they're explicitly not saying you have to do it a certain way, which means I would encourage you to find the path of least resistance. And sometimes the path of least resistance is using a formula for an area of a shaping organ. Here, although we will learn how to find this antiderivative and use the fundamental theorem of calculus to find the area for this, that's not what we're going to do right now. Right now, we're going to say, well, hey, I know that y equal to the square root of 36 minus x squared looks like the top half of the circle. And if it's easier to see that, you can square both sides and then bring the x squared over to the left and say, oh yeah, x squared plus y squared equals 36 is the full circle centered at the origin with a radius of 6. So this part here is the top half of that, because if y equals the square root of some stuff, y has to be positive. So this function here looks like the top half of a circle whose radius is 6. And then what this integral says is we want the area under y equal to the square root of 36 minus x squared between x equals 0 and x equals 6. Great, I can shade that in. X equals 0 is right here. X equals 6 is right there. So I want everything under that curve from as far left as 0 to as far right as 6. But that's just a quarter of a circle. So we can say that this area is in fact 1/4 of the area of a circle with radius 6, which is pi 6 squared. And then we can simplify that and get 36 divided by 4, which is 9 pi. So when we're just talking about area, we can kind of use whatever method might be the most convenient. Now, we are certainly going to talk about the fundamental theorem of calculus because most functions are not so easy to deal with. But let's talk about one more where, again, I would recommend maybe not trying to find an antiderivative and use this theorem that we haven't even talked about yet. So another example that you might think about drawing is something like the integral from -2 to 12 of the absolute value of, sure, 2x minus 8. There is a way you could do this without drawing a picture, but it's probably easier to just draw a picture. Absolute value functions are not too terrible. They look like V's, is what I always think. And really, to draw the absolute value function, you have to find the bottom of the V, which is where the function would be equal to 0. So what does x have to be so that y equal to the absolute value of 2x minus 8 equals 0? Right, x needs to be 4. That's the bottom of the V, as I would call it. So great, now I'm going to draw this. And I'm going to go from -2 to 12. I don't need to be as precise as I'm trying to be right here, but I ended up being precise, so whatever. And then I'm just going to draw something V-shaped. And then all I want is the area under this curve from -2 to +12. Or said another way, all I want is to find the area of these two triangles. Great, I know how to find the area of a triangle. So this right triangle here, right meaning the one on the right, and it's also a right triangle, meaning it has an angle of 90 degrees. But specifically, I meant the one on the right here. The area of that blue triangle is going to be 1/2 the base times the height. The base is just 12 minus 4. And the height is going to be, I need to plug in 12 to my function to find it. So I plug in 12, 2 times 12 is 24, 24 minus 8 is 16. So this point here is 12, 16. And that's going to be 8 times 8, which is 64. And then we do the same thing for this other triangle here. The area of the red triangle is going to be 1/2 the base, which is 4 minus 2. And the height, if I plug in -2, 2 times -2 is -4, -4 minus 8 is -12, and the absolute value of -12 is +12. So the area of that is going to be 1/2 times 6 times 12, which is 36. And then we add them together, and say that the total area is going to be 100. So the integral from -2 to 12 of the absolute value of 2x minus 8 is 100. And certainly when people ask you integral questions involving the absolute value, most of the time their expectation is that you would approach it like this. You draw the picture, get a couple triangles, and find their areas using the formula for the area of a triangle. It doesn't mean we couldn't do it another way, and we certainly will talk about later on how you would do it a different way, especially if your function was something else less nice in the absolute value. But for now, this is how we do it. Yeah.
I was just gonna ask for clarification what you plugged in on both sides of the.
Oh, sure. So like define these points here.
Yeah.
So I'm taking my left endpoint, -2, and plugging that into this function here. So if I plug in -2 there, 2 times -2 is -4, -4 minus 8 is -12, and the absolute value is giving me the +12 I'm getting right there.
Oh,
Similarly, over here, I plugged in 12. 2 times 12 is 24. 24 minus 8 is 16. That's I'm getting the 16 there.
so where did you get the 6 at the bottom?
6.
The area of the red triangle?
Oh, sure. So the difference here between -2 and 4 is 6. And the difference here between 4 and 12 is 8. Yeah, no problem. Also, just as a point of interest, my absolute value was the absolute value of a linear function that has slope of 2. And when the slope is 2, the height of your triangle is going to be twice as much as the base of your triangle, which happened for both of these triangles. If the slope had been 3, then the height would have been 3 times the base, which is just kind of interesting. It happens all the time. It is not a coincidence. It does happen because of how these things look. So it's not like a coincidence that you're getting like 1/2 times 8 times twice 8 and 1/2 times 6 times twice 6. That is perfectly normal and expected to happen if your line is 2x minus something. All right. Oops, dropping pens. Okay, let's go ahead and look over here. Yeah. So let's talk about the fundamental theorem of calculus. I really, really wish this clock that was right in front of me, that's easy to read, said the right time. I'm like, oh, it's only 3:26. No, it's not. It's 3:47. That said, if we get to what? The end of 4 o'clock? Right? 4 o'clock? Is that the time we actually end at? What time do we start? We ended at 4:30, right? 4:20? 4:30. Okay, we ended at 4:30. We started at 3:10. We ended at 4:30. Great. If it's 4:31 and I'm still talking, say, hey, James, it's time to stop. Or you'll just start leaving because you might have places to go. As I said before, just in case you might be your first day here, if you need to leave, that's fine. If you have a class that starts at 4:10, you need to go to it, or you have a test later, please leave. You don't need to like ask me for permission. You're welcome to come and go as you please. Same goes for using the restroom. Please just do what you need to do. It's totally fine. So fundamental theorem of calculus. Part 1. I was building up the suspense. Not really. All right, so let's talk about how we want to imagine this for a second, because we're going to try to give us an idea of why the fundamental theorem of calculus actually works the way it works. Big picture, though, is that the fundamental theorem of calculus really just says the derivative of the antiderivative is the function you started with. That's kind of it. If you started with whoops, I'm going to trip on this pen. If you started with a function and you took its antiderivative, and then you took the derivative of that, you'd be back where you started. That's really the whole entire story. Maybe not the whole entire story, but the gist, what's important to remember. So, well, let's kind of do this thought experiment, for lack of a better word, to help us see why this might be true. So let's let y equal the integral from a to x of f of t dt. And this is going to be the area under the function f of t between or from t equals a to t equals x. And just to set things straight, we typically imagine A being a constant and X being a variable. So X is going to change or range over some values. A is going to stay set as just whatever A is. A. And so then we're going to try to give some meaning here. We're going to suppose that F of t equals the velocity of a runner at time t. Then the area under y equal to f of t represents the distance that the person has run over that time period. Distance traveled by the runner. Or specifically, before I say more, I mean, so I believe a lot of you have had problems that you've done where you've had like, so again, apologies if this is not correct, but I think some of you showed me problems where you have like, you're given some table of like a time interval from 0 to 60 seconds. Does that sound familiar at all? Yeah. And then you're given like speeds that either a motorcycle or is going or something is going, and you're asked to approximate the distance traveled by finding the area, by finding the length of time multiplied by the speed. And time multiplied by velocity gives you distance. If you go 6 feet per second times 2 seconds, you're going to end up having gone 12 feet, and the seconds cancel out. That's the same idea here. We're just adding up all the area under a curve where the curve is representing velocity. We're essentially multiplying a velocity by an amount of time, which is giving us an amount of distance. So here's what it means specifically. Y equal to the integral from a to x of f of t dt is equal to the total distance traveled by the runner from time equals a to time equals x. Yeah, let's use a new piece of paper before I start trying to draw things here. So here's what this looks like graphically. So here's my f of t, which is the velocity of the runner. We're starting at A. We're going to some x. This is t measured in whatever unit of time we might like. We're going to say seconds, although this would work using any units we wanted. And our velocity measured in meters per second. Okay. So I'm looking at this area, and what I really want to look at is a little rectangle. Oh, this pen looks okay. It's the one I stepped on, yeah. So this little rectangle right here. The area of that rectangle. Well, let's just talk about the units for a second. The units are time in seconds, right? Some elapsed time. And the height is some amount of meters per second. So we're getting meters, which makes sense, right? It's coalescing with what we're kind of talking about here, that the area under this curve should be a measure of the distance traveled. All right, so if y is equal to the distance traveled, well, if you know someone's position as a function of time, you can find their rate of change, their velocity, by taking the first derivative. So we can say here that dy dx is equal to the rate of change of the distance at time equal to x. But that's the same as the velocity at time equal to x. But we know another way of finding the velocity at time equal to x. We specifically said f of t is the velocity of the runner at time t. So if we want the velocity at time equal to x, that should be f of x. Okay, we're going to put it all together now and get the result that we're looking for. We're going to say that, can I fit this all on one page? Maybe. So there's our y up there, and we just said that the derivative of that is equal to f of x. Or in other words, or in other expressions, the derivative of y, which you can't see I'm pointing to, the derivative of y, the integral from a to x of f of t dt is equal to f of x. Or as I said in the beginning, the derivative of the antiderivative of the function gets you back to where you started. You might say, well, James, it's f of x, not f of t. Okay, fine. Yes, we have to use a different variable there to make it all work nicely. But the idea is still the same. You're starting with the function f of t, you're anti-differentiating it, you're plugging in x, and you're taking the derivative, and you're getting back f of x, which is essentially the same function, just with a different letter or a different variable. Questions so far? Okay. So, how much do we want? Yeah, we'll do that. One of the points, so really, I would say the first part of the fundamental theorem of calculus, so I should, yeah, so this is FTC part 1. The first part is useful. It's kind of it's the more important. What am I looking for here? It's the thing that gives us the rest of the stuff. It's the idea that's important here. But in practice, the second part of the fundamental theorem of calculus is really what we use more of to actually calculate things like the area under the curve. That said, we still have to know how to deal with this. So let's do a few examples where we use this. Maybe if I can move a piece of paper, maybe. So let's say we have the following. Y equal to the integral from 4 to x of t cubed dt. Yes, I can. What's dy dx going to be? There's absolutely no work to show here. That's not true. We could totally show work once we talk about the second part of the fundamental theorem of calculus. But for now, we can just say, well, the derivative of the antiderivative of the function is going to be x cubed. Which might feel a little unsatisfying, but it is true. We'll come back because I feel like I want to show you some stuff, but I really feel like I need the second part of the fundamental theorem of calculus to show it to you. Yes. Well, yes, if we are saying that this is the same sort of situation. So we're saying, right, that would be true if we were saying that this integral is representative of distance traveled. But more broadly, we're just kind of using functions in whichever way we like. It doesn't have to represent velocity and distance, although it certainly could. Right, exactly. We did the, so I'm going to show you the work, even though we haven't talked about the second part here. But essentially what you could also say is that this integral, if you actually did the antiderivative of this using the second part of the fundamental theorem of calculus, the antiderivative of t cubed is going to be t to the 4th over 4. And then you're going to evaluate that between 4 and x. Plug in which limit first? Top, always the top first. So you get x to the 4th over 4 minus 4 to the 4th over 4. And then if I want to find the derivative of that, right, because that is what my y is equal to, well then, if y is equal to x to the 4th over 4 minus 4 to the 4th over 4, then the derivative of that, well, the derivative of x to the 4th over 4 is going to be 4x cubed over 4. And the derivative of 4 to the 4th over 4 is 0, because it's a constant, and derivative of constant is 0. Oh, look, that's x cubed. So when you do the antiderivative and then you do the derivative, you end up back where you started. But we had to change the name from t cubed to x cubed because we end up using a different variable at the end of this process. So let's go over there. Yes, yeah, but I'm also never going to write this out because it's true that we can do this long way sometimes, but sometimes, like if your function was y equal to the integral from 3 to x of e to the t squared dt, e to the t squared is famously not antidifferentiable. There is no antiderivative of e to the t squared or e to the x squared, whatever you want to call it. End of story. Like, don't look for it. It's not there. You cannot find a nice function whose derivative is equal to e to the t squared. It doesn't exist. And there are lots of functions that, like sine of t squared, also does not have an antiderivative. There's lots of weird functions that don't have a nice antiderivative. But if I want to find the derivative here, well, whatever the antiderivative would have been, its derivative is going to get me back to the function I started with, which is just going to be e to the x squared, which is great. So we're going to move on because I feel like this part's always a little bit more confusing without more explanation. So let's talk about the fundamental theorem of calculus part 2. And do I have enough room on this piece of paper? Not really. We'll come back. Maybe. So the fundamental theorem of calculus part 2. The important part. The one you're really going to use like for the rest of your calculus career. Not that you will never use part 1 again. It will probably show up sometime. But part 2 is really where it shows up. So we have the following. Since the derivative of the integral from a to x of f of t dt is equal to f of x, right? That's just part 1. Then here's what we can say. If we anti-differentiate both sides, we can say that the integral from a to x of f of t dt is just equal to capital F of x. That's an antiderivative of little f. Plus c. Right. All we're really doing at this point on those categories is we're anti-differentiating both sides. We're saying the derivative of this function is equal to that function. So the antiderivative of this side, which is just this, is equal to the antiderivative of that side. But they might differ by a constant because antiderivatives can always differ up to a constant. Right? If you take two antiderivatives, you always slap it on a plus c because they might not be exactly the same. All right, but then we're actually going to figure out what this is. So if we let x equal a, then the integral from a to a of f of t dt, I'm just going to plug in a and get f of a plus c. Can anyone tell me, can anyone show me on their fingers, can everyone show me on their fingers, what the integral from a to a of f of t dt is? How much area is under f of t if I start at a and end at a? Oh yeah, no fingers. That's 0. Right, we started at a, we stopped at a, we got no area. But that means we can figure out what that constant is. If I subtract f of a from both sides, that constant is equal to negative f of a, the antiderivative evaluated at a. And then we get the result we want. If we let x equal b, then the integral from a to b of f of t dt is equal to f of a, sorry, not f of a, f of b, right? I'm plugging in right there, f of b plus c, but c is negative f of a. So that's capital F of b minus capital F of a. Or as I would prefer to write, doesn't matter if I use t's or x's here, the integral from a to b of f of x dx You can write it this way, but a more typical way of writing it is writing it as the antiderivative capital F of X evaluated from A to B. Which S is equal to capital F of B minus capital F of A. So this is the thing we've been alluding to for a while. That if you want to find the net area under the curve F of X between X equals A and X equals B, you can find that by finding the antiderivative of your function and then evaluating that antiderivative at the top endpoint minus evaluating it at the bottom endpoint. So, for example, like those two examples we started class, we did the limit definition of the integral of. If I wanted to find the integral from 0 to 1 of the square root of X dx, instead of doing all the work we did using that strange partition, instead we could say, well, I'm going to write this as, I'm actually going to rewrite it as the integral of X to the 1/2. And then I'm going to use the fundamental theorem of calculus part 2. I'm going to anti-differentiate X to the 1/2. I'm going to get X to the 3/2 divided by 3/2. Do I need a plus C? It doesn't hurt. Although I don't need it. You'll see why. Evaluated from 0 to 1. I'm going to rewrite this to make it nicer. That's going to be 2/3 X to the 3/2 plus C, evaluated between 0 and 1. We plug in the top limit first. We get 2/3 times 1 to the 3/2 plus C, minus we plug in the bottom limit second. 2/3 times 0 to the 3/2 plus C. Notably, the C's will always cancel here. This C and this C are the same, and C minus C is 0. So when you're doing a definite integral like this, we don't ever need a plus C. You're welcome to write one. It won't harm you, but it's superfluous. We don't need it. So we end up getting here is 2/3 times 1 minus 0, which is just 2/3, which is the same answer we got before. When we did that way back when, if you look back in your notes, you'll see that we got 4/6, which ended up being 2/3. Let's do the other one as well, which I forgot what it was. Let me look back and see. Here. We started way back in the beginning. Yeah. Similarly, we could use the fundamental theorem of calculus part 2 to find the definite integral from 0 to 2 of x squared plus 4x. When we did it before, we got 32/3. I hope we get the same answer here. We should, unless I made a mistake before. So I'm going to anti-differentiate this. I'm going to get x cubed divided by 3 plus 4x squared divided by 2, evaluated from 0 to 2. We're going to plug in. So I'm going to plug in 2, and I'm going to get 2 cubed over 3 plus 4 divided by 2 is 2. So I'm going to get 2 times 2 squared minus 0 cubed over 3 plus 2 times 0 squared. Point of interest or something to be aware of. A lot of the time when you plug in 0, everything becomes 0. But not always. Like e to the 0 is 1. Cosine of 0 is 1. Lots of things evaluated at 0 don't just end up being 0. So make sure that when you're plugging in 0, you don't just automatically assume it's all going to turn into 0. A lot of the time it will, but not always. So this ends up being 8/3 plus 2 times 4, which is going to be 8/3 plus 24/3, which is, yay, 32/3. Yes. You might be. So what I would anticipate, if teachers are anything like my teachers when I took 21B, is there might be one question where you're asked to actually use the limit definition to evaluate it. And it might be an extra credit question if your teacher likes to give extra credit. But most of the time, nobody wants to grade that kind of question. To be perfectly, I don't want to grade that. It's terrible because there's so many places a person can make a mistake. And there's a lot to look through. So, but really that's a question that's better to ask your actual teacher because they're the ones who actually know what they're going to write. And some people are more demonstrative about what they're going to do. Right? Some people will tell you more than other people will. So never hurts to ask. Some people are like, no, I can't tell you. Some people might actually tell you, oh yeah, that might be an exam or it might not. So that's what I would do if I was really concerned about it. It's kind of like the limit definition of the derivative. On your first exam in 21A, there was probably a couple of questions about the limit definition of the derivative, using it to actually find a derivative, something that you could have used like the power rule for really easily. The same thing might be true on your first exam. You might have to find the limit definition of the integral of something relatively easy, probably something like x squared or x cubed from 0 to 1 or 0 to 2. So if you think you might have a problem like that on your exam, practice it. Do some examples. You know what the answer should be now, right? You all could pretty easily figure out that the integral from 0 to 1 of x cubed dx is going to be x to the 4th over 4 from 0 to 1, which is going to be 1 to the 4th over 4 minus 0 to the 4th over 4, which is just 1/4. Great, we did it the short way. Take a few minutes on your own sometime and do this one the long way, using the limit definition, and show that you also get 1/4. And yeah, I would say also make sure those right, you're going to need to use whichever formula you need to use here, right? It's probably the sum of k cubed equals n times n plus 1 over 2 quantity squared. So practice that. All right, let's go. So we'll do more of these in a minute. But let's go back to the fundamental theorem of calculus part 1, because that part I feel like was a little bit dicey. But now that we've at least seen this, we can be a little bit more sure about what we're doing. So let's say I want to find, for example, and I personally like to write it like this. So you could write it as f of x equal to the integral from -3 to x of, thank you, sine of t dt, and then say I want to find f prime of x. But what I'm typically going to write is just the derivative ddx of the antiderivative from -3 to x of sine of t. To me, that's just a more convenient way of writing. All right. So we should be able to answer this in one shot. The derivative of the antiderivative of sine of t is going to be sine of x. End the story. Could you show more work? Yeah. Should you show more work? Not unless you're asked to. The work we could show, though, is that this is going to be equal to the derivative of, well, let's use the fundamental theorem of calculus part 2 to evaluate this seemingly looking definite integral. So the antiderivative of sine of t is negative cosine of t. We're going to evaluate between -3 and x. We're going to get the derivative of negative cosine of x minus negative cosine of -3. And I turn the minus into a plus. Then we take the derivative. The derivative of negative cosine of x is negative sine of x. And the derivative of cosine of -3 is not sine of -3 or negative sine of -3. It's 0. I don't know what cosine of -3 is, but I know it's a constant. I know it's a never changing value. It's always going to be the same thing. If something never changes, its rate of change is 0. Its derivative is 0. So look, we get back to where we started. So for relatively straightforward ones like this, where your bottom thing is some constant and your top thing is x, your derivative of that antiderivative should just be the function you started with. Or as I said, it should just be the integrand, but with x's instead of t's. So one more easy example. Bless you. Sorry, if you sneeze, I don't say bless you. I still present height or however you want to take it. Let's say the derivative of the integral from 2 to x. Sure, let's do that. Let's do 3t squared over t cubed plus 4 dt. Plus, I don't want to find the antiderivative here. I could. It's doable. We don't have to. We should just be able to say that this is going to equal 3x cubed over 3x squared, sorry about that, over x cubed plus 4. Now I'll point out, if you wanted to find the antiderivative here, we have to do a little bit of thinking. If I look at this, there is a function that's going to work. The antiderivative here is the natural log of t cubed plus 4. Let's check that. If you took the derivative of the natural log of t cubed plus 4, you would get 1 over your stuff. So 1 over t cubed plus 4. And then what do I have to multiply by? Which is, anybody? I think we're good to go. So the derivative of the natural log of t cubed plus 4 is equal to that. Oh, I mean, it's going to work out perfectly, right? We're going to plug in the x's. We're going to get the derivative of the natural log of x cubed plus 4 minus the natural log of 8 plus 4. And then when we take the derivative of that, we're exactly going to get 1 over x cubed plus 4 times 3x squared minus 0. Just like we said it should be.
The chain rule is 3x squared.
Right, exactly, because of the chain rule of 3x squared. Speaking of the chain rule, sometimes these fundamental theorem calculus part 1 questions are more complicated. Specifically, sometimes the thing up there is not just x. It could actually be a function of x. So for example, maybe, let's see. I could say, what's the derivative of the integral from -1 to x cubed of cosine of t dt? Oops, you can't quite see that, sorry. All right, well, let's do this one the long way so that we can see what's happening. So and then let's make it even more interesting. I'm going to change that -1 to a negative pi over 2, just for fun. No, I really don't like that choice at all. Let's make it a pi over 3. Good times. Okay, so we're going to anti-differentiate cosine. We're going to get positive sign evaluated between negative pi over 3 and x cubed. We're going to plug in. Always the top first. So it's going to be sine of x cubed minus sine of negative pi over 3. I will point out, because I chose this specifically, sine of pi over 3 is root 3 over 2. Sine of negative pi over 3 is negative root 3 over 2. But really, I just wanted to show you that if you're plugging in a constant here, you're getting a constant out. And so when we take the derivative of that constant, that part's going to be 0. The derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. So it's a little bit more complicated when your limit of integration is a function of x as opposed to just x itself. You have to plug in whatever you have up here and then use the chain rule and multiply by the derivative of that. We end up with cosine of x cubed times 3x squared. So we're actually going to revamp our fundamental theorem of calculus part 1. So here's the more general version. So the more general version of the fundamental theorem of calculus part 1 says that if you find the derivative of the integral from a to g of x of f of t dt, instead of just getting f of x, you're going to get f of g of x times g prime of x, as evidenced by the example that we just did. So let's do one that looks really funky. I know, it's everyone's favorite. So let's say we want to find the derivative of the integral from 1 x to the fourth of e to the t over 1 plus t to the third. I do not know how to anti-differentiate that. It's probably impossible. Doesn't matter. We don't have to know. The fundamental theory of calculus tells us we don't need to actually find the antiderivative. We just bypass it. We say, well, everywhere I see a t, what am I going to write instead? X to the fourth. So I'm going to have e to the x to the fourth over 1 plus x to the fourth cubed. And then what do I have to multiply by? 4x cubed. And we're done. That's all there is. Nothing more to do. Okay. No, good. Don't be sorry. Go ahead.
So where the T was, you just literally put in the X to the fourth. So the goal is gonna be the top one.
You asked the perfect question. Thank you. That's what I was waiting for. So what if it was on the bottom? What if we had the integral from, say, let's make it the natural log of x to 2 of 7t squared plus cosine of t. I don't like the variable on the bottom. Well, we don't have to leave it on the bottom. So if you change the order of integration, what happens to the whole thing? Negative. So we can definitely, so what I'll say is you don't need to actually rewrite it. Most people skip this part. I'm gonna write the part we would usually skip and write this as negative the derivative of the integral from 2 the natural log of x of 7t squared plus cosine of t dt. Most people would probably just skip that and say, oh, the variable's on the bottom. It's going to be the negative of what you would have normally gotten, and say that we're going to get negative. I'm going to plug in the natural log of x for every t, and it's 7 times the natural log of x squared plus cosine of the natural log of x. And then all of that has to get multiplied by what? One over x, the derivative of the natural log of x. But we could totally skip writing that part there. Sorry, that's terrible. You could skip writing that part there and just go, oh yeah, the natural log of x on the bottom, so we know get a negative, and then it's just the same usual thing. You plug in whatever your function of x is for every t, and then at the end of the day, you multiply by the derivative of your function of x, which is 1 over x. Okay, and then for the most terrible version possible, what if the top and the bottom both have functions of x? It's really not more terrible. It's equally terrible. I mean, you could argue it's more terrible. So let's say we want to find the derivative of the integral from e to the x plus x to x cubed of, let's make it not too awful, 3t to the 5th plus tangent of t dt. Oops, you can't see that. Okay. The short answer is you plug in the top one, you multiply by its derivative, you subtract, you plug in the bottom one, you multiply by its derivative. The long version of this answer is you can break up an integral literally anywhere. In fact, yeah, we'll show that in a second. You can break this up anywhere you like. So I'm going to break it up at a convenient place. I'm going to say 0. I want to point out, I did not say that 0 has to be between the two intervals, the bottom and the top. It can be. It's lovely when it is. Doesn't have to be. You can break up an integral anywhere. So I'm going to write this as the derivative of the integral from e to the x plus x to 0 of my terrible function, 3t to the 5th plus tangent of t, dt, plus the integral from 0 to x cubed of 3t to the 5th plus tangent of t dt. But then this one is not how I'd like it to be written. I would really like this one to have the variable on top. So I'm going to switch the order of integration and change the sign to be negative. And then so I don't have to write this 2 more times, I'm going to write this part first and say I have the integral from 0 to x cubed of 3t to the 5th plus tangent of t. And then instead of plus this, it's gonna be minus this with the order of integration switched. Then those look like kind of the normal way of doing it. The derivative of this is just gonna be plug in the x cubed, multiply by 3x squared. So we're gonna get 3 times x cubed to the 5th plus tangent of x cubed times the derivative of x cubed minus same deal here. 3 times e to the x plus x to the 5th plus, I should have picked a nicer function, tangent of e to the x plus x, all times the derivative of e to the x plus x, which is e to the x plus 1. But we could have skipped all of this writing in the middle and just said, oh yeah, we're going to plug in the top thing. Sorry, you can't quite see that anymore. We're going to plug in the top thing for t and then multiply by the derivative of the top thing, which is 3x squared, subtract, plug in the bottom thing for t, and then multiply by the derivative of that. So that's the worst version of this kind of, where the top and the bottom both have variables. But it's still very manageable. It's still the same idea. You just have the additional thing of subtracting the bottom part as opposed to just getting 0. Oof. Okay, 426. So let me say, yeah, oh, sorry, that's it. There are some properties of integrals that we haven't really talked about, which is too bad we only have a few minutes for me to do that right now. But the one I was referring to specifically is that if you have the integral from a to b of f of x dx, you can break that integral up literally anywhere you want. So for any c, you can say, oh, I'm going to go from a to b. I can go from a to c and then c to b. And the way I'm imagining that in my head is certainly where c is between a and b. Let me show you what I mean. I'm imagining this as the area under f of x from a to b, and then breaking that up at some c in between the two. So that this integral here is the area in blue, and this integral here, oh, sorry, I shouldn't do that, is the integral, is the area in red. Sorry, I'm used to hitting my, sorry. Okay, so, which adds up to the total area from a to b of f of x. But c didn't have to be between a and b. Check it out. I think this is one of the neater things that happens in this particular property here. So I could have drawn this in a similar way, except my pen is dying, except here's a, here's b, and here's c over here. So now I'm saying that the area here from a to b is equal to the area from a to c. Watch this for a second. I mean, obviously, if you have to go, you have to go. It's equal to the area from a to c plus the area from c to b. Oh, but c to b is out of order. So what that means here is that here, if I want to think of this the right way, the integral from a to b of f of x dx is equal to the integral from a to c plus the integral from c to b. But what I should really do is I should rewrite this part as the negative integral from b to c. And then it all makes sense that this area under the curve from a to b is equal to the total area from a to c minus the area from b to c. Totally works out. So this formula is true as long as things are integrable, continuous, whatever. For any c, you can pick a c between a and b, but you don't have to. And sometimes it's convenient not to. So that's what I was trying to say. And I will stop talking because it's 4:29.